Okay, that's good. Um, so what I wanted to show you um, is um, some stuff. Actually, strangely, I've already consigned this lecture to the past. That's a bit forward of me. Um, but I did write a whole bunch of stuff. So this is the video from last time is now online, and a nice ask window for you to try recreating the stuff that Fred and I did in the code. And I also wrote a bunch of notes, which I hope you will find useful. So this chunk of stuff is about proving propositions. And what is a proposition? It's some kind of statement that makes sense after I wonder whether. That doesn't necessarily mean you're ever going to find out, but it's something that it makes sense to wonder about. Some people will tell you a proposition is a statement which is either true or false, and they are just wrong. It is presumptuous to imagine that a statement that you might wonder about will turn out to be true or false. It might be more complicated than that. But you could hope it might be true or false, but it might not actually be true or false. Okay? We're in a different world from the CS106 world of Booleans, which are either 0 or 1, because those things are on little bits of wire that are either at 0 volts or 5 volts, and there are machines called transistors that just bloody test that stuff. We can't necessarily do testing. We have to think about it. In particular, you've already been proving propositions that talk about infinitely many things, that are universal properties of functions you've defined, that the statements have variables. The variables could take infinitely many possible values. You can't possibly hope to test them all, but you can think about it. And there are kind of proofs we can give. So we saw last time a bunch of logical connectives. We saw and or and implication, and we related those to the kinds of structures that we work with in programming. And if you remember in week 9, I asked you to write a lot of programs involving data structures that represented either pairing or choosing or all of that sort of stuff. It was a bit like multiplication and addition. Your tutorial homework will drop shortly after this lecture, and I'm going to ask you to do all the same stuff all over again, only with proofs. Just by way of pointing out there aren't actually all that many ideas. Normally, we wait till 4th year to tell you that there aren't very many ideas. But I thought I would just let slip in 1st year. Okay. So I also wrote some stuff about how to make friends with a logical connective. So something like and or whatever. So here's my checklist for how you make friends with logical connectives. Well, you need to know their informal name. Actually, it's good to know. Some people might do. There might occasionally be the odd bit of Latin that gets thrown in. So it's sometimes good to know the fancy name as well as the English name. So there's a thing called and, which some people will call conjunction. And there's a thing called or, which some people will call disjunction, that kind of stuff. You need to know what its notation is, and you need to know what you would do if you were asked to prove it. And you need to know what use is it to you when you're told it, right? So it's a game. Sometimes you're asked to prove things. So, give evidence for a proposition. And sometimes the boot's on the other foot. You're told this proposition is true, and you need to figure out how to make use of it. So you need to know both of those things. And then after that, there's a bit of pragmatic strategy. So there's lots of chat there, and we'll see more of that this time. I don't think it's worth plowing through it because it will all appear just in the course of doing stuff. So less jaw, more action. Actually, before we get to the cliffhanger, let's just do a little reprise of one that's easy, just by way of showing stuff. We do that one. Do you want to do it?
Yeah, sure. Have you moved this distracting little green thing out of the way?
I wish I knew how.
It's less distracting down there, I think.
Right. Okay, cool.
And how do I? Okay. So we've stated the proposition we want to prove, which says that if we know P, then we're hoping to be able to prove not P, right? So if P is true, then it's impossible that not P is true, right? Okay. And the way we did these things last time was we said, okay, the kind of top level connective here is an implication, right? And the standard way to prove an implication is to say by implication introduction. And then I send that to ask. And we see that now our goal has changed a little bit, right? So now, given the assumption, a given P, and we have to prove the conclusion not.
So just by way of strategy, it's sometimes good to have muddy spectacles, right? Don't look at all of the details. The key thing you need to see is that this is something arrow something. That's all you need to see to know what to do. Because if you're asked to prove something implies something, by implication introduction is always a good move, right? You never have to think about it. You see the arrow, you do implication introduction.
Yeah. Okay. So now we are in a slightly better situation in the sense that we know more things, right? So we started off knowing nothing, being asked to prove this thing. And now we know that P is true. We get to assume this for the rest of the proof. And we have to prove not P, right? Okay. And then kind of in the same way, when we see a not, there's one canonical move we can do. If we want to prove a not, then we should do that by not introduction. Okay. And then the state of the goal changes again. So now we are given the thing we are trying to negate, but we have to prove false, right? So we have to prove that it's impossible that not P is true, in the sense that if not P was true, then false would be true. And if false is true, then cows can fly, right?
Yeah. So false is the proposition that means this whole situation is impossible. Right. This can't be happening to me. Whereas not P is merely the proposition that P is impossible.
Okay, so now there is no canonical way to prove false, right? I mean, that's kind of the point of false. So now we can't just do the obvious move and not think. Now we have to start thinking, right? So before there was a canonical thing to do. We saw an implication that we wanted to prove, so we did implication introduction. We saw a not that we wanted to prove, so we did not introduction. But now there is no canonical false introduction because that's the point of false. So now we have to think, okay, how can we show that the situation is impossible, right? So we know that P holds and we know that not P holds. That's kind of contradictory information, right? On the one hand, P is true. On the other hand, not P is true. So the way to use this canonically is that if we know not of something, then it's enough to prove this thing we know doesn't hold in order to get whatever we want. And in this case, we want to get false. So I'm going to say from this.
Yeah.
And of course, I can't use your keyboard.
Control. Yes.
Okay, I'm just going to type it in for now. So I'm saying from not P, and then I send that to ask and see what ask tells me back. And then ask is clever enough to see that we have P given. So we've already proven this thing, which we know is not true. And that's all we need in order to say, okay, this is impossible.
Right. So here's a piece of strategy for you. When you are given not of something, here not P, that gives you a particular power. It's a particular kind of teleportation. At any point where you're having a bad time proving something, you can say, I'd rather prove P. Because how you use not P is to say, I can show this whole situation is impossible by proving P. So we got to this point. We were asked to prove false. We didn't like that one little bit. We said, I'd rather prove P. Unfortunately, P was already true. It's okay.
So why don't you prove the other one?
Right. So you're used to, so this is known in the trade as double negation introduction. And it works out sweetly. This thing here is known in the trade as double negation elimination. And it's a bit more vexing. Okay, let's do it. Or at least let's try. Right. First of all, we see something arrow something. We think no harder. Implication introduction. Okay. Now we're being asked, prove P. We don't know P, so we can't. There's only one thing we do know, so the only thing we can possibly try is to use the thing we know. This amounts to saying, I'm being asked to prove P, and what I'm basically saying here is, I'd rather prove not P, which is a bit of a strange thing to say. But okay, I'm now being asked to prove not P to show the situation's in P. And again, I don't have to think. I'm being asked to prove not. I do not introduction. And now I've been given a proof of P. If only I was still trying to prove P and hadn't chosen to prove not P instead, I'd be laughing. But instead, I'm not proving P. I'm proving false. And I'm in a bit of difficulty, right? And I can try again. I can try again and say, okay, I'll try and see what happens. The only thing I know that might get me out of here is to try and prove not P again. But then I can be given another copy of P, but I'm just going around in circles. So this goal this goes harder than it looks. In fact, for now, I'm going to give up. We'll come back to it.
Maybe again worth comparing to CS106, where if a wire is not 0, then it has to be 1, right? So if we know that the wire is not 1, then in fact it is 1 in that situation.
Yeah, so this proving business is a little more subtle and strange than this testing business that you might be used to. Okay, so I'm also going to interested in thinking back to, again, the stuff we did in week 9. So let's look at what happens on the programming side. So once again, I don't know if you remember, but here we go. We've got these 4 data types. There's a data type which I called 0, which has no values in it. So if you're asked to make a value of type 0, you're in trouble. And if someone claims to have a value of type 0, they're a liar. There's also a data type called either A, B, where you can deliver a value of type either A, B, either by providing an A or by providing a B. You know, it's good to choose obvious names. So that's kind of our data type version of OR. And then on the other side, we've got a data type called 1, which contains 1 value. So it's very easy to make a value of type 1, but it's also very predictable which value it is, right? It's very, if someone says, I've got a value of type 1, I'll give you 3 guesses what it is. You shouldn't need the other 2. Meanwhile, there's also this data type that plays the same job, the same role as AND, which is called both. And to give a value of both A, B, you have to give a value of in A and a value in B. So let's look at some programming that's a bit like logic. So for us, the thing that in programming, the thing that plays the role of not is a function returning an impossible value. So here, for example, we're hoping to prove, or we're hoping to write a program which says, if we know that A is true, if we have evidence for A and evidence that A is false, then we ought to be able to blow up the world. Do you want to do this?
Okay. Let's blow up the world. Yeah. Okay. So now I have to remember how to program rather than to prove things.
Well, it's the same.
But it's indeed. So I have my function not boof. I have my input x, which has this type. And I'm kind of interested in what this input is, right? So it has type boof of something. So I think it probably is a pair. So I'm going to inspect this x and say from x. And then ask is telling me, well, x actually is a pair of some x and the y, say. Okay, or maybe. So then I have to think a little bit. So what is x? X is the first component of the pair. So it has type A. And y is the second component of the pair. So that's this function, which takes a's and turn them into the type which has no inhabitants, right? Which is a bit suspicious. So if I take my y and I give it the x as an input, because x is an a and y expects an a as an input, then I should have an inhabitant of 0. And that's what I want, right? So I think I can say this is y applied to x. Okay.
Okay, so that's a programming version of that story. But let's do the corresponding proof. We want to show that it is not the case that both P and not P are true. Okay, let's play this game. Right, we're asked to prove a not. Brain switched off, just do not introduction. Okay. We are given an and again, it's a free hit always to take an and apart. So we don't have to think yet. We just take that thing apart. And now we're given the pieces separately. So I've just done the same move as Fred did. Here it was from X, giving a pair, and now it's from P and not P, giving both P and not P. And then I'm being asked to prove false. I don't want to prove false. I'd rather prove P. And we're done. Okay, so that's great. We know that P and not P can't be true. But that thing has a friend. The thing that says, well, it must be the case that something is true or it's not true. So, do you want to do this one?
Okay. Right. So what does that translate to over in the programming world? Well, or was this either type, and being false was being a function into zero, right? So the statement that something is either true or not true is the statement that we can write a program of this type, which says that, well, either B, I have a value of B, or I have a value, a function that turns B's into zero. So how do I define this? Well, I have a standard way to introduce things in the either type, right? Because the either type has these two constructors. I could either say, okay, I want to construct something on the left by supplying an A, or I want to supply something on the right, namely a B, right? So in this case, the left situation is a B, or the right situation is a function B to zero. Any suggestions what I should do?
I mean, B, it corresponds to some logical statement. You don't know what the statement is, and we're asking you to tell us whether it's true or false.
I mean, I suppose I could start trying something. So, okay, I have two choices. Let's try the first choice. So I say left, and then here now I have to give an element of B, right? But I don't know what B is. B might well be zero, in which case this is really hard. So left is not the right choice, I think. Okay, let's try the other one. And then here, I now have to give a function from B into zero, right? But again, I could be so unlucky that B is actually this one type, for example, in which case I have to give a function which turns this it element into an element of zero, but there are no elements of zero, right? So actually going right is not a good choice either, right? I can't do this if the B is the wrong one. So what should I do, Connor?
Give up.
Okay.
Right. Yeah. So the problem here is that to give a value in the type, in an either type, you have to give at least one bit of information. You have to come off the fence and say yes or no. I mean, this type is actually an outrageous statement because it says for any B, for any type B, without knowing what it is, you can say whether it's true or false. And it's a bit much to say you can answer any question, even if they're going to tell you the question. But here they're not. Okay. So from a computational perspective, this business be or not be, is highly suspicious. If you think of it as actually promising you a bit of information, it's not going to happen. So, okay, round about now, the thought police, especially in the mathematics department, are sending the SWAT team. Because in the rest of the world outside this room, be or not be is so bloody obvious as to be boring. And we're here to tell you that it isn't. But don't panic. Let's see what happens on the proof side. I mean, it's the same situation. I'm trying to prove some kind of OR. There are two ways to prove an OR. One is to choose to go left. So I say by or introduction left. Then I'm asked to prove B. And I don't know how to do it. So, okay. I'm stuck. If I go right, then I'm asked to prove not B, which is nice because I can say by not introduction. And now I'm given a B, which I would have really liked a moment ago. But now I'm being asked to prove false. And I have no way to get out of this. So by the ordinary rules, I'm in trouble. Okay. So how on earth are we going to get out of this situation? There's got to be something extra that allows mathematicians to do mathematics that doesn't correspond to anything that lives in the programming world. Well, there's an extra ingredient that we haven't told you about. We'll tell you about it now. The mathematicians believe that to make something true, it is enough for it to be unbearable for it to be false. I mean, so here I'm going to say, I don't know why P is true, but I can't stand the idea of it being false. So what I say is by contradiction. This is the extra rule. So instead of actually delivering positively a proof of P, instead I'm given not P and asked to blow the world up, right? It's just like, instead of saying, here's why it's true, we're saying, if it's false, we can't stand it.
Is it worth doing that at the top level, just to very clearly show what's going on?
What, you mean one level out?
Yeah.
Sure, could do that.
No, I mean to do a prove.
Oh, right.
Yeah,
yes.
Contradiction.
Prove Q by contradiction. Right. Give a not Q, prove false. That's how the rule works. Takes the current goal and it gives you the opposite of it and asks you to blow shit up. Right. Okay. So now we're in a wonderful situation because we are given not P, which you can read as the right at any time to say, I'd rather be proving not P. And as I've just been given not P, I think I'd rather be proving not P. And we're done. I'm trying to fill you with a sense of dissatisfaction that this works. But if you're if you want to put it this way, I'll tend to sort of put it this way, is that, you know, if you had, if you were an omniscient deity, then you would know whether things were true or false. And this would be completely problematic because you could test everything, right? It's the only reason why this is unsatisfying is because we have limited resources, right? So kind of from a theoretical and beautiful position, there's absolutely nothing wrong with this at all. From a deeply practical position, it promises you magic bits that you can't have. So that's a distinction that we're going to draw. And the point is, though, that if you don't actually need the bits, there's nothing to worry about. Or at least nothing too bad to worry about. Okay. So let's go back to B or not B and do a bit of a tag team on it. I'll start. Okay. So here, we're trying to prove B or not B. Instead of starting with by picking a side, I'm going to start by contradiction. Apart from anything else, it gets me out of having to make a decision.
This is how it normally works, though, right? You try to do it without contradiction first.
Yes.
You explore, see what happens. Maybe you can just prove it.
Yeah.
You realize you're stuck. There's no way to do it. Then you delete all of your attempts and you.
Yeah. I mean, so there's sort of various metaphors you could use. It's like you try and if you're Pac-Man, you run away from the ghosts. If you're not going to escape from the ghosts, you eat a power pill, and the ghosts can't get you, but you are no longer corporeal. So, yes. So yeah. So here we just ate the power pill, and now we have incredible superpowers. So I need to prove false. When you need to prove false, you would rather be proving something else. All the negated things we've been given are opportunities to prove something else. So yeah, a not given is a getaway car, right? No matter what situation you're in, you can be in a different situation by froming a not. So I'm going to from this not. Okay. And now I've got to prove B or not B. And it looks like I've gone around in circles, but I haven't, because I know something that I didn't know before. Okay, I got to choose whether to go left or right, and breaking the habit of a lifetime, I'm going to go right.
I mean, you could again try going left first, right?
I don't want to. I don't want to.
But you're going to get stuck very quickly if you do.
Yes. Well, yeah. So I'm going to go right. And the reason I'm going to go right is because I'm seeing an offer of swag. Okay, I'm being asked to prove not B. So I can do not introduction, that's a no-brainer. And now I've been given a B, but I have to prove false. I'm stuck. Fred, can you get me out of this one?
Yeah. So again, it looks like where we were before, right? Where we said, okay, I'll try to go right. And then we were given a B, but we had to prove something impossible. But the difference is that we now have this thing as well. So we still have the getaway car, right? So let's just use it again. Okay, I'm glad I can copy paste. So I'm going to say from this. Okay. So since we know that not B or not B, we can get anything we want if we can prove B or not B, right? But now we're in a good situation because we have been given a B on our journey, right? So here I can this time say I'm going to go left, except with less shouting. And going left means I have to prove B, but we have been given B, so we are actually done, right? So first we went right, then we were asked to prove something hard, and then we restarted and went left, so to speak.
Yeah, it's sheer bank robbery. I mean, you know, I went into the bank, I stole a B. I gave up trying to prove false, but I gave the B to my friend. But you know, if it feels like cheating, it should. But you know, that's how it goes. You know, the devil says, I'll prove not B. Thank you for your B. Actually, I've changed my mind. I'll prove B. I mean, all right. So under these circumstances, I think we'll do these last two and then have the halftime break. Yeah, so in some situations, if you've seen the truth table for implication, you'll see that implication is often considered to be the same thing. So A implies B means either A is false or B is true, is often how it's seen. I have a friend who explains it by saying, if I promise my kids that if it's sunny, we'll go to the zoo, then what's the possibility? Yeah, what are the possible outcomes, right? When have I broken my promise? When have I kept it? If it's sunny and we go to the zoo, I've kept my promise. If it's raining and we go to the zoo anyway, I've kept my promise. If it's raining and we stay home, I've kept my promise. I've only broken my promise if it's sunny and we don't go to the zoo. Is kind of the idea here, but there's something going on. So let's see if we can show that both ways round, right? So what I'm trying to show is that not A or B is equivalent to A implies B. So I can't remember which way around is the hard one, but actually I can. So I'll do the easy one. Right.
Maybe it's also good to put in some spurious brackets around not A here, just to be very clear what this means.
Yes, these brackets are not strictly necessary. And also I'll put these brackets in just to be totally clear. Okay. So, proof strategy. This is, I mean, all I'm seeing is this arrow. And I already know I'm going to do by implication introduction. All I'm seeing is this arrow. And already I know I'm doing implication introduction. So that was, I didn't have to think. That was where two moves. So now I'm at given A, prove B. and I need to figure out what to do. I don't immediately know how to prove B, but I have some useful information, namely not A or B. That means there are two possibilities, and I should investigate them one at a time. I do from not A or B, and my proof splits into two cases. But one of the cases was just given B. Right? In one of the cases, B is already true. I've got to do with the other situation where now I'm given not A, and I have to prove B, but I know A. So that's pretty cool. I don't want to prove B. I'd rather prove A. And I'm done. So how about the other way around?
Yeah. So just a small comment. So another way to see this is that we know that not A or B is true, right? We'll be given this. And what Connor is really doing here in the last case is showing that it's impossible that not A is true, because we also know that A is true. So we basically are saying this case can't happen, and we're only in the good case where B was actually true, right? Okay, but let's try to do it the other way around. So it's the same two formulas, but we've changed the direction of the arrow, right? So now we are given an implication, and we are asked to prove that either not A is true or B is true, right? So the only thing we see at this point is that there's an implication. So we'll do an implication introduction. Okay, so we are given this implication, and we are asked to prove this or. So now, if we're not using contradiction, then we are really asked to make a choice here, right? We have to go left or we have to go right. But again, we don't really have any good evidence for either of these. So if we go left, then we have to show that it's impossible that A is true. But all we know is that if A is true, then also B is true, right? So that doesn't really help us get to false. And if we go right, we have to show that B is true. But all we know is that if A is true, then B is true. But we have no reason to believe that A should be true either, right? So a direct proof seems really hard here, which suggests that maybe we should try to do it by contradiction. I'm kind of tempted to use this previous thing we proved, though. Is that something?
It's a thing. You could do that if you want.
Yeah. So I could do it by contradiction and then see what happens. But we have proven that if we allow ourselves to use contradiction, then we know B or not B for every B, right? So I could try and just see A or not A.
Yes.
So if I send this.
Yep. So it's a thing to remember. When you have proven something in ask will let you use any substitution instance of it. So ask is quite happy here to recognize that that this is B or not B with A substituted in B's place.
So we've proven that previously, so we are entitled to it. And why did I do this? Well, because I saw that I want to show not A here. So maybe I'm lucky. Not A is already true. Or A is true, in which case I should be able to use my implication here to turn A's into B's and prove the B instead, right? So I think I'm now in a good place. So here, I can just say by or introduction left, because in this case, I have to deal with the fact that not A might be true, okay? And in this case, I've been given that A is true, so I'm going to go right? Because it would be silly to try to prove not A when I know that A is true. Okay, and then I have to prove B, but I have this implication here. Right? So of course, rather than appealing to this previous fact we proved, I could have done a contradiction again and kind of reproved that fact. But I think it's a bit clearer to just pull that out as a separate statement.
That's entirely reasonable, and it's liner upper for what's going to happen in the second half. So there you are. You've seen how with the assistance of the extra magic that is contradiction, you get back to a world where propositional logic obeys the same rules as just, the logic that you have with bits, even though something really quite different is going on. And this is the first time I've ever actually presented logic to first years with a clean conscience. Normally, I just tell all the usual lies. Anyway, it's pretty much 5-2. So it's 7-2, but let's reconvene at 3 minutes past and just chill out for a bit or nip out for a bit. and yeah, we'll probably keep recording and not bother editing it out. But yeah, halftime break. I certainly
Oh ja, das ist eigentlich ist auch Chinese. Oh wow, there's two Chinese in there.
So know that as what? No, that is. You know what that is? The very far side of the room. Five rows down, actually. They've got one thing on party guys sitting behind them. It's like a group of guys in the front. Yeah. It's the one right at the wall with dark light. Alright. Actually, this is quite helpful because I can just look at this. Waarom always
Exactly why I
Yes.
mentioned it too early.
Okay, folks. Hopefully that was a useful little pause. But let's get back to it. What we're going to do in the back end of this lecture is another classic bit of reverse Turing test business. We are asking you in this chunk of CS103 to learn to prove stuff in propositional logic. And it's once again the embarrassing situation of trying to teach people to do things we can just program computers to do, no problem, right? You lot are so much more difficult. So we want to show you a variety of strategies for beating the shit out of these problems that guaranteed to succeed, but you won't like it. I mean, that's to say, if you've got, so the thing about the computer is that it doesn't get bored and it doesn't get upset if it explores a bit of search space that isn't productive, right? It's like playing Sudoku. It's really annoying when you make a wrong move in Sudoku and you have to rub stuff out and try again. and you know, you feel bad about that. Whereas computers can just try all the possible combinations, and if they're wrong, so what? It'll find the right one sooner or later. Bam, done. Deeply emotionally unsatisfying, but highly effective. Right. So we're going to show you some deeply emotionally unsatisfying, but highly effective ways to prove anything we throw at you. The problem that I'm going to set for Fred is to prove that P implies Q or Q implies P, which of course is a very, if you think of implication as causation, then this is extremely weird. But implication isn't causation. So
so at face value, this says something like either us going to the pub caused Trump to be elected, or Trump being elected caused us going to the pub. Right?
I know which of the two it is.
And, okay, so maybe in that case it's so we shouldn't really expect to be able to prove this directly, because again, we are asked up front to decide, is it the case that P implies Q or Q implies P? And it's really hard to do that before we know what P and Q are, right? So we shouldn't expect a direct proof. I mean, we could try saying, okay, I'm going to go left, and then I'm going to do an implication introduction, but then I'm faced with proving Q, just knowing P. And the other case is very similar, right? So I don't think I will make a proof that will make me satisfied here. So I'll just resort to more violent methods, right? So one thing I can do, so like we did in the previous proof, we can always say, okay, let's just make cases on A or not A for any A we want, right? So here, I could make a case on Q, for example. So I say either Q or not Q. Okay, and then I get these cases. And then in each one of them, I can just say, well, let's make a case on P as well. P or not P. Copy this. And make the same case down here. And then I'm given these 4 different situations to be in, right? Where here Q is true and P is true. Here Q is true and not P is true. And here not Q is true and P is true, and not Q and not P, right? And then I can just look at these cases and see which one do I like here. So here, both P and Q are true. So actually both going left and right looks kind of okay, right? So why don't we go left just to break? Okay, because I know that Q is true. So I'll just do an implication introduction, and then I have to prove Q, but I know Q, right? And here, in this case, well, I still know that Q is true. So I can go left, and then an introduction. In this case, I know that P is true. So I'm going to go right, because in the end, I want to prove P here to the right. Okay, and here, I know not Q and I know not P. So I don't really want to go either right or left here. But on the other hand, well, it doesn't really matter where I go again, because wherever I go, I'm going to be given either a P or a Q, right? So let me go left again. Okay, so now here I'm given a P, but I also know not P. So not P, and I'm done, right?
Right.
So it's not a very insightful proof, in the sense that it doesn't really tell you why P implies Q or Q implies P, right? It's just saying we're trying all the possibilities, and in all cases, it must be the case.
Yeah. So this strategy amounts to just writing out the truth table for the formula and checking that it always works out true. Right? What does the truth table do? It tabulates all the possible truth values for the variables, and then you figure out what that means for the statement as a whole. And that's what we do here. We use excluded middle, as it's called, so B or not B, for each of the variables to get, 2 to the 2 possibilities here. And then we just check that in each of the cases, it works out. So you can see already, right, that it's not a lot of fun, but it is going to work. So you have method number 1 of beating a proof to death if you have to is just to consider all the possible cases individually. It's not, it's not fun, but it's going to work. So that means that's marks in the bag, right? Marks in the bag.
So maybe one thing to point out is that, so here I try to not think at all, more or less, right? But actually you can see that in this first case, as soon as I knew Q, I didn't actually need to also look at P in this case. So you could make a slightly better proof by first splitting on Q, and then you can actually get rid of all of this, right?
Yes. You can, you know which way to go once you know whether Q is true or not. You know that if Q is true, you can go left. If Q is false, you can go right.
Okay.
So
right,
sometimes, a blend of brute force and observation is useful. Okay. So that's cool. I want to show you a different method, which is kind of an ancient traditional thing. Which here's one I prepared earlier. So I'm going to be very careful not to show you the top of this file. Should I have reloaded Emacs?
Should have pulled.
I didn't. Okay, sorry. I'm not going to do it now. Right. So what we're talking about is that Fred on the train in fixed the syntax highlighting. This given should be bold. Right. So here's a fun fact. In ask, if you've already proven something and you feel like proving it again, the only proof that you need to give is the statement and the word given. That tells ask, here is something you should already know. And if ask agrees that it already knows it, it will turn prove into proven. Otherwise, it will say, I haven't been given that. This is how marking works. Is that we check if after you've done your best, the things that we wanted you to prove are now given. So we can at least automate that much. So we can't do kind of, did you get it half right? Did you make some good moves? But we can do, did you get it all right? Pretty straightforwardly. Okay, so here are a bunch of things that I have proven. And the reason I'm not showing you the proofs is because they're your tutorial homework. But I'm going to show you a particular method for reliably proving all the things, right? So the thing about classical mathematics is that all proof is refutation. You know, there's just no matter how positive the idea may sound in the first place, you can always reduce it to blowing the world up. You know, that's entertainment. Oh, by the way, quick rant. You may have noticed that politicians and celebrities accused of bad behavior will claim to refute allegations. So I'm here to say the word refute means to disprove, to show why something is not true. It does not mean merely to deny something. And the politicians and the celebrities use this word incorrectly to suggest that by refuting something, they have shown themselves to be innocent, when in fact, they have merely claimed to be innocent. And then what happens is it gets reported by lazy journalists in the third person. You know, Boris Johnson refuted the allegations as if he disproved them when he merely denied them. This is how it works. Words slip in meaning, and combined with third-person reporting by lazy journalists, people escape. You know, people weasel their way out of situations. It's very, very noticeable. So we're going to do refutation, but refutation meaning actual disproof. Okay. So so everything turns into refutation. Okay. And so okay, you see, I'm proving the same thing that Fred just proved. In this version, in the refutation game, the idea is that we are only happy when we're proving false. We used to not like proving false and do anything to get out of it. Now we like proving false. If you're not proving false, you sure as shit want to get back to proving false as soon as possible. Okay, so that's how it goes. Now you see on my handy piece of paper, which I'm afraid is not visible to the Zoomers, but you might have to imagine. Maybe you can do it.
It's in the camera.
It's in the camera, but it's probably a very tiny little thumbnail for the Zoomers. You make a big table like this, right? So the question is, how are we going to get to false? We've been given some stuff. Some of the stuff we've been given is true, and some of the stuff we've been given is false. So we look at our givens. Some of them start with not, some of them don't. So here, we've been given not of P implies Q or Q implies P. So in my nor column, I'm going to write P implies Q or Q implies P. So I'm trying to blow up the world. There are some things I know are true and some things I know are false. I know this is false. Okay, so far? Now, I have chosen to prove a collection of handy facts which help me play this game systematically, because they explain how to make progress towards false when I'm given either that something is true or that something is false, for all the kinds of something that we've got knocking around. So I need to look no further than to see in my nor column, I've got something or something. So I know which rule to use to make progress. I'm going to go from And here's my how to get to false with not something or something. So I copy and I paste. I have to remove the given. And now I have to be very careful. I have to make the right substitution. So the thing that's in the row of A here is P arrow Q. So substitute. And the thing that's in the row of B is Q arrow P. Substitute. And maybe I'll just remove a little bit of space. Okay, so I've chosen the right rule. I make me move, and then I've got to prove the conditions. My immediate next move is and introduction. And you'll notice this is something and something implies false. The first thing is the thing that I chose was guaranteed to be there because that's why I chose that rule. So I'll only get one sub goal. And then I do implication introduction until I can't anymore. So I'm back to proving false. So I've played, so this is round 1. And what I've done is I've disposed of this thing. Just going to cross it off. Let's see. I've been, so what I've done is I've made maximum use of this thing. And I've been given some new stuff. So I've got rid of one thing from my NOR column, but I've got 2 new things. I've got P implies Q, and I've got Q implies P. Those are 2 new things I know are false. And I don't have to worry about the old things anymore. So what's the deal here? Is that anytime I've got a complicated formula in either column, I have a rule that will get rid of the complicated formula and replace it with simpler formulae. So you can see, if you look at what's here in all of these things, you can see that there's a bunch of sub-goals. There's a bunch of things that are all about proving false and using things that are either A or not A, B or not B. The complex formula gets simplified. So you know, each round, we're going to take a complex formula and simplify it, and that can't keep going forever. So this is an algorithm which is bound to work. Okay. So for our next round, I can see I've got 2 givens. It doesn't matter which one I pick. In fact, you pick. P implies Q or Q implies P. The first one. Okay. So our second round is going to go for this thing. I've got a rule, or rather a handy fact that says what to do when I know not of an implication. So I'm going to paste that in, get rid of all this space. And here I've got P for A and Q for B. I'm just gonna, so this is round 2. And I'm gonna just mark that I've crossed that one off. Okay. And now I do and introduction again. And the thing I was targeting disappears by implication introduction and implication introduction again. And I'm back proving false. So that's the end of round 2. And I've crossed out P implies Q. And I know some new stuff, namely I know P, and I know P is true, and I now know that Q is false. And I could start getting clever here, but what's the fun in being clever when you can carry on being stupid? So we've got one formula remaining. Q implies P. So let's do round 3. Oh, sorry about that. Slippery fingers. So that's gonna go from, this is, I should label this round 3. And this is going to go from, again, it's a false implication. So I want the rule for refuting false implications. And this time, A is Q, B is P, A is Q, B is P. And then I do an and introduction. And the first subgoal disappears by construction. I do as much implication introduction as possible. And a back proving false. And that's the end of round 3. I have, wherever it's got to, I've crossed this one off. And now I can update my table. What have I got? I've been given Q, and I have been given not P. So that's nice. Okay. So the deal is, but what you'll notice is that we no longer have any complex formulae in the table. We've got all the complex formulae that we had. We've kind of wrung all the good juice out of it. Now we've just got variables and their negations knocking around, or literals as they're called. So this is as good as it gets. We're not going to make any more progress. We have either won or lost. And the deal is, we have won if there is a variable which occurs in both columns. Because that means the same thing is both true and false. So that's going to get us out of trouble. And we're lucky here, in fact, that we're spoiled for choice. So I'm just going to say by not P, and whoop, no, not by not P. I meant from not P. From not P. And we have won. So this is victory, and could have chosen not Q. Okay.
So just to point out the obvious things, that these comments that Conor are writing are just comments for us, right? Mark doesn't care about these things.
Yes.
So that goes for the round annotations and for the crossing out of the formulas. That has no formal meaning. Right?
Yeah, I'm just giving the structure of how we're playing the game. So that's an approach to systematic refutations. You keep track of the things you know are true and the things you know are false. And if you've got anything which is not either just a variable or the negation of a variable, then you have a rule to split it up. So sometimes Sometimes you get 2 sub-goals, sometimes you just get 1. We were lucky in this one. We never got, the problem never split in 2. There is always the potential, just like, okay, so when we were just doing the B or not B for all the variables, then we were splitting into exponentially many cases without even thinking about it. Right, here, you win some, you lose some. Yeah, it's I thought that would take longer.
It's worth showing one that doesn't work, maybe.
Right, shall we well, try and prove something that isn't true?
Yeah.
What should we try and prove that isn't true?
Okay.
Oh yeah, why not? So let's go wrong. Prove P or Q. All right, but let's play the game as I outlined it. Okay, we're not proving false. We want to get out of that as soon as possible. So we start off by contradiction, which have to spell. Okay.
Before we go any further, can I have a little comment saying this should not work or something?
Yes,
Always.
sure. Also, I should get myself a new piece of paper with, right, so, okay, what do we know? We know that P or Q belongs in the null column. Okay, do you want to do this?
Yeah, okay, I can try.
I'll mind the
Right.
.com.
Yeah. So okay, so let's try to follow the method. So the game is that we are given a not of something which is not a variable, right? So we go up and look at the kind of facts we have. And we see that we have something that says what to do if you have a not A or B. So I'm going to copy this. And go down here again. Say from this thing. And then I'll do the substitution by hand. So P, A is P, and B is Q. Okay, let's see what else says about that. Okay, so I'll do that by and introduction. And then I take care of this by implication introduction. So hopefully you can start to see a pattern where we're always doing the same thing every time, right? So you could imagine you could automate this.
So we've crossed out P or Q, and we've got separately P, Q in the null column.
Right. Okay.
And
we're back to proving false. But now we are kind of stuck, right?
yeah, we've got only variables in sight. We're down to P and Q here, and we've got nothing here. So there is no variable that occurs on both sides. So we're screwed.
So this is how we know we get stuck with this method, right? We get down to
Yeah.
just atomic things here, but no more moves to make, and there's no contradiction in something in both columns.
Yeah. So this is also reassuring, because once you get here, you know you're beaten, as opposed to just kind of trying stuff and hoping that if you kind of just work a little harder, it's going to come out. It's not, you know, we're screwed. You know. So, okay, let's
maybe one more comment that actually this kind of gives you an idea how you would falsify this formula now, right? Because it tells you that if P and Q are both false, then in fact P or Q is going to be false. So I guess we're not going to prove this here, but you can kind of read off a counterexample from the end state where you were unhappy.
Yeah. So it's also the case that there's a large industry in using extremely clever tricks to play this sort of game super efficiently. You know, in the last, half a century, human beings have got very good at programming computers to do this. Shall we have one that's, it's always nice to go out on a victory.
Yeah.
Shall we prove something that's actually true? Yeah, I can't remember what it is. Is it what? P implies Q implies Q. Which way? Can you remember what it is? Look it up. We're just gonna Google something. This was also going to be in the homework, but now it's not. So,
Right. P implies Q implies P. That's a P.
uh-huh.
And all of this implies P.
That's pretty wild. Right. So this is kind of exciting. It says something like if P has a consequence means that P is true, then P is true. That's just sort of wild. It's also something, you'll notice that there's no hint whatsoever of not in this picture. But actually, well, let's try and prove it by being clever. So it's an implication. So we start with implication introduction. Now we need to prove P. Now we've got something that proves P. Now I have to prove P implies Q. I do by implication introduction. Given P, and I need to prove Q. But I don't have anything that proves Q. I've got some facts. I've got something that P holds under some conditions, and I've got that P just holds. But that doesn't get me all the way to Q. So I don't know what to do. In fact, this is one of the notorious things that you need to some form of contradiction to prove. It's called, this is Peirce's law. Trying without contradiction won't cut it. Okay, let's comment this out because it's useful information. And let's instead just use contradiction. Let's just use this method. Okay. So at the moment, we've got P implies Q implies P implies P. Okay. So we go up and we find our collection of things. Here is what we do if we have been given a negated implication. So this is round one. And I'm going to go from this fact. And I got to be a little bit careful doing my substitution. This whole thing is A. Substitute that. Substitute that. And B is just P. Okay. And I can cross this one off. And now what's the table showing us? Okay. So now we've got this implication in the I column, and we've just got an atomic P in the NOR column. Okay. So that means we've still got work to do. We got a positive implication. So that means we want this thing. This is round two. We're going to go from that. And this time, A is P implies Q. So substitute, and B is P. Substitute, substitute. Okay. Oh, what did I do there? Oh, I didn't get rid of the question mark. Classic ask cock up. Okay. And now we go by and introduction. And now I've got two sub goals. The search space has split. So you're going to need to chop the piece of paper in half. So we've got our first situation where we actually have two sub goals, but we can use the same method.
What do we have? So we have positive P.
So on the left, we have negative P implies Q.
And on the right, we have a positive P.
And on the right, we have a positive P. Okay, so you can see that we're winning on the right because we've got, so in this sub goal here, we have a P and a not P. So this one is dad. In the other one, we still have a complex formula. We've got a negated implication. So we go and grab the rule for a negated implication, which is this thing. I should, of course, cross this thing off. So we've got this thing, and here A is P. And B is Q. Oh, and I've forgotten to delete the question mark again. Okay, we do and introduction, implication introduction, and implication introduction again. And here we have to prove we've been given a positive P as well as a negative Q. Yeah. Okay, but that's good news because we back ages ago we were given a not P and now we've got a P. So again, we are home. So there we go. We have beaten another, frankly, rather puzzling goal to death just by the application of this algorithm. What can I do for you? Because I didn't have Q. So if I look at my table, I could see the thing that occurs in both columns is P. So that's to say it's the thing I know is both true and false. So that's the thing that lets me win. So it turns out the Q is kind of a red herring in this problem. It's just a question of which side of the arrow the P's are on that makes this work out. So it's always nice. Let's just that was round 3, and that was getting rid of that thing. So that's to say we've shown you a bunch of individual ways of doing logical deduction. We've shown you that contradiction gets you back into a world where any kind of instincts you might have from truth tables are restored to working at the cost of their computational meaning. And we've shown you that if you organize the right collection of helper results, that you can be totally systematic about beating propositional goals to death. This is very firmly a class of problems that we give to the machine rather than ones we do ourselves. So you folk have to learn to mash these problems to make so that you're allowed to let computers do it instead. But it's very cool. Now, it doesn't take us terribly long to get off this high, right? You know, this class of problems that just uses Boolean connectives, you know, computers can do it, but we don't have to push it terribly hard to get somewhere that that computers can't handle nearly so well. And as you might expect, I'm going to say that's a very good thing, right? You know, if it was easy for computers, we'd be out of a job. So it's reassuring that that this kind of basic logic shuffling is something we can get done for us so that we can get to the real problems. Okay, so
I would also say that there's a leisure argument in the sense that if all problems were solvable by computers, then it wouldn't be any fun solving problems. So it's also good that there are things that you need to be a bit creative to do.
Right.
We'll get to those things very soon.
Yeah. So so I will set up the tutorial homework file for you real soon now, and it will consist of the logical versions of the programming problems you had in the week 9 tutorial, which you should just be able to blast your way through. And you know that you should not need contradiction to solve any of them because you were able to write the programs. However, I'll also ask you to prove this collection of helper results, which will entitle you to use this systematic method to beat all the problems, all the propositional problems to death. Okay, it's 10:02, but we ran out of material about 20 minutes ago. So we dropped a tutorial problem. Thank you very much for getting up so early and coming here in 3 dimensions. Thank you on Zoom for showing up anyway. I guess we better stop the recording if I can figure out how.